Right. So today for our lab, we are going to look at experiment number 3. Okay. So last week, what did we look about? What was our experiment last time?
Half adder, full adder, half subtractor, full subtractor.
Subtractors and full subtractors, right? Okay. And adders also. Good. Thank you for responding. Now, today we will be taking it to our next experiment, and that is nothing but called realize parallel adder subtractor using 7483 chip, and to convert BCD to XS3 code and vice versa. I think this parallel adder and BCD to XS3, it's covered in your theory classes, isn't it? Is it covered in your theory classes? Students, be responsive. Okay, be active. Yeah.
Parallel adder and subtractor, I don't think it's
Okay.
No, sir.
Uh,
Only half order,
Only half adder is covered. Okay.
half order and full
Uh,
adder.
Cascaded adder. Cascaded adder. When you actually connect the adder in series.
yes, sir explained about 2 minutes of
Hmm.
that.
Hmm. Fine. Fine. Okay. So, nevertheless, we will be looking into the practical point of view. Okay, as to how these will be implemented. Fine. So this is going to be your circuit diagram, and these are your components, which is 7483, 7400. Okay, 10, your trainer kit, and your patch cords. Okay, I will not get into these numbers because you're all very familiar with this, and we have seen this in the previous labs, right? Can someone just quickly tell me what is this 7483? Yeah, 7483
It's a IC number,
IC number.
series number.
Okay, fine, but it's used for, what is it used for? Okay, so this is used for your adder purpose. Okay, for your adder. So this is going to perform your parallel adding operation, right? You have inputs, which is A1, A2, A3, A4, then your another set of inputs, because you need to add with something, right? So you need A and B. So we're taking 4 bits, okay, 1, 2, 3, 4, and 1, 2, 3, 4. Then similarly, you're going to get 4 outputs along with your carry out. Now let us just take one simple example, okay? And before we get into it, just try to know the configuration of these IC. Okay, as you have seen here, you can see that you have a 1, 2, 3, 4. These are all your input pins. A1, okay. Then you have your A2, A3, and then your uh, A4. Yeah. So accordingly, you will have your corresponding 1, 2, 3, 4, and some also 1, 2, 3, 4. Right. So properly see the pins, okay, and accordingly connect. The most common mistakes performed by many of the students is that you try to swap off with VCC and ground. Okay, that shouldn't be done. You just make sure that you don't swap VCC and ground. Now, in order to know the pin numbers, okay, you can always check for the data sheet of 7483, and you will get to know what is the pin number of these. Okay, ultimately, you know that it's going to start from here 1, 2, 3, 4, 5, 6, 7, 8, right? 9, 10, 11, 12, 13, 14, and 16. So this is a 16 pin IC, right? So you will have your inputs A and B. I'm just giving a random number, 1100 and 0011. So if it's added with a 0, I'm going to get a 1. But if in case, okay, if in case there is another 1 here, then this will be a 0 and carry out will be generated, right? That's what we have seen here. So I'm not getting a carry out, so my C out is 0. Okay. So if control input is 0. Next, if I give a control Or if I'm trying to generate the carry out, how will it generate when it has two ones? I don't think so there's any doubt in the addition of binary numbers. Is there, students?
No, sir.
Yeah, this is very simple as it is, right? 0, 0. 0 plus 1 is 1, 1 plus 1 is 0, and carry out this becomes 1. This arrow should actually come here. Okay, fine. Okay, next, now subtraction. How will you do a subtraction? You'll be using 2's complement. How is 2's complement? How do we do 2's complement? Can someone unmute and respond? That I've seen extensively in your basic electronics, right?
You convert the subtractor to one's complement and then add 1 to it.
Add 1, right? So it becomes a 2's complement. Very good, Darshan. So we are looking at, converting it to zeros and ones. We are swapping. So that is nothing but called your ones complement. Okay, so your B value, okay, your B value is going to be swapped with zeros and ones. That is your ones complement. To that value, I'm going to add 1. Okay, so that is going to be my 2's complement. So what I'm going to do with this, I'm just going to add them, right? Okay, so using this operation, we can actually get to know how the subtraction is done. Okay, so this is going to be your pin configuration. Yes, this was what I was talking about. Now you have your pins here. Okay, so you can see that the last pin is B4, B4, right? So this should be a 16th pin. Okay, yeah, B4, 16th pin. Okay. So if you can remember this, it will be good. So that which input, okay, A1, A2, A3. So which inputs are going into which IC pin numbers. This is very important. Okay, so once you know this, then everything becomes very easy, and you can try and understand, okay, how the circuit actually is implemented, right? So now that we know how to perform an addition, and now that we know how to perform a subtraction, okay, so so we know that manually we should be getting these values. So we try giving those values here, okay, b1, b2, b3, b4, all these values I try to give in here. And of course this is for your adder, right? So I'm making use of the adder itself to perform this subtraction operation. Okay, right. Now, how many of you are aware of this BCD to XS3 converter? What is meant by BCD to XS3?
If you add 3 to BCD, it becomes XS.
Yes, exactly. Now, Badri Ram, you can unmute.
Yes, sir.
Yeah, and now you can tell me, why do we need to do this code conversion? Are code converters really important?
So your voice is breaking, sir. I can't hear.
Are code converters important? Why do we need code converters? Okay, guess he has a network issue. Someone else wants to pick it up? Maheshwar, can you answer that question? Or Bhavya, would you like to pick up that question? What is the use of code converters? Bhavya?
Yes, sir.
Yes. Can you tell me the application of code converters? Why is it needed?
Sir, because it is decimal, I think so, sir.
No.
BCD knows.
Generally, I'm asking, generally, why are code converters used? Bhumika?
Yes, sir.
Yes. Why do you think we need them? You there?
Sir, to convert like into the code which we want, like encoding or decoding something like
Exactly,
that.
exactly. Right, Bhumika, thank you. So students, one thing here we should understand is code converters are used for secure communications, right? So in order to hide some data, okay, in order to make sure that your data is private, okay? So we make sure that we employ the use of converters. So this BCD to XS3 is one such conversion, okay, where I will tell I'm going to add 3. I can even add 4. I can even add 5. So that is my code, right? So instead of 3 here, I can make it even 5. So I can call it as BCD to XS5. Okay. So I am going to use a code and I will send information in some form. Okay. So once we have a truth table, okay, how are we getting this truth table? I think all of you are very much aware. Just for the benefit of all, okay, concentrate on your left hand side of the table. You have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Can someone tell me why are we using only till 9? Can I use even 10?
Because BCD is from 0 to 9.
Exactly, right? Good. So we are only using numbers 0 to 9. Okay, greater than that, what should I put in my output? Suppose there is a 10 in my input. So in my output,
Don't
what
care,
am I
sir.
going? Sorry,
Don't care.
don't care. Very good. So we are just going to don't care the outputs from after 9, right? So now that we know how this table is developed, okay, what is the next step once we have a truth table?
K-map.
K-map, exactly. So I am going to load up these values into the K-map and I'm going to get an equation. And that equation, is it going to be a modified equation or is it going to be an optimal equation or is it just going to be an unmodified equation? What kind of expression are we obtaining from K-map?
A simplified expression.
Exactly. So we are going to get a simplified expression. So which means that is the most fine-tuned expression, which is most simplified and which can be implemented. So I will have those equations. So based on those equations, I'm going to use my um, De Morgan's theorem, right? And I will convert them to my standard gates, which is the universal gates, which is NAND conversion. So I think all of you are very much aware of NAND conversion using the bubble method as well, right? So you can insert a bubble and you can convert it to NAND uh, gates. So you should have this truth table. Truth table is to be loaded into K-map. Once the K-map is loaded, do the proper grouping. Once proper grouping is done, then you will get a fine equation. So that fine equation you can implement using your logic gates. Once you implement using logic gates, you can actually use the bubble method and you can convert it to your universal gates. Is there any doubt with this, students?
No, sir.
Okay, fine, good. So similarly, what we are going to do is we are going to see how the reverse happens, which means XS3 to BCD. So your input here, okay, is going to become the output and the output is going to be input. So these two tables are just swapped, okay. So this will be coming here, okay, and XS3 will be going here. Okay. The values, all the values are going to remain the same. Fine. So let's just have a look at it. So this was your input, isn't it? 0, and I'm getting 3. So here 3 becomes my input and I will be having 0. So how will I do this? How will I enter into the K-map? So you can value this as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So you can put this into a K-map. Now since this is 4-bit, so which means I'll be having 16 squares. So in the 16 squares, okay, we will be valuing only up to 9. Okay, only up to 9. So greater than 9, you can actually put them all as don't care, and then you can do a grouping. So the order of that is going to be in this form. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to be in this form. Okay, that's going to be the order of your K-map. And once you get a fine equation, okay, a normal implementation and conversion to your NAND circuit is as shown like this. So here what you can see here is, you have the pin numbers, right? So which means you will be using the pin number of which IC. Are we using the pin number of 7483, or are we using the pin number of the NAND gate IC?
NAND gate.
Exactly. So we are going to use the pin number of NAND gate IC. Here we are going to use the pin number of your adder. Okay, 7483. So here it's all XOR gates internally. Okay, fine. So this is about your experiment today, and I will be sharing in this video. Okay, and also I'll be sharing in the video of the practical as to how you can develop. Okay, and what I want you to do is, you can have a look at this video that I'll be posting, and you can make note of your observation. Okay, and I want workouts of K-map, and I want to see how these equations, and just let me know if these equations are right, if the circuit is right. Okay, so you can put up in your observation notebook, and you can do the same conversion to your XS3 to BCD as well.